work with today, we're going to continue to work with significant digits, but we're going to work with powers and roots. There's a little bit of different notation dealing with powers and roots, some of which you're familiar with, some of it maybe not. We're going to cover these topics today. So, two main objectives today. The first one is, I want you to become familiar with the notation used to represent powers and roots. There's a couple of different ways that you can write powers and roots. I want you to be familiar with both ways and know exactly what they mean and how to work it on your calculator, how to use your calculator. And I want you to be able to use your calculator to evaluate bases with positive or negative exponents. And I think I lied. I think I said there was two objectives. I've got a hunch that there's more, judging by all the space that's still there. Must have forgotten one. So if you don't already have your calculator handy, you'll want to grab that. We'll be using it quite a bit today. And powers and roots are really just different ways of writing the same general concept. Any root, square root, cube root, any other type of root, can be written as a power, and any power can be written as a root. And there is one more. By the end of the day today, I want you to be able to use your calculator so that you can efficiently evaluate roots regardless of what the indices or what the index of each root might be. So the first thing we need to do is we need to take care of a little bit of terminology. Make sure that the terms that we're using are all the same. We're going to start out with powers. First one, the expression. An expression is basically any numeric value or a mathematical statement that's not part of an equation. So 5 to the third, that's an expression. It's an example of a base. We call the lower number there the base, and we call the upper number the power. Of course, that 3, some of you probably know, is also called an. We could say it's 5 to the third or power. 5 to the third power or 5 cubed, but that 3 is also referred to as an exponent. And it is probably review to you that this is really just an efficient way to represent multiplication that's done over and over again. In this case, of course, 5 to the third power just means we're going to take 5 and it'll be a factor with itself 3 times. So 5 to the third is 5 times 5 times 5. So before we go any further, take your calculator out and we'll deal with this simplest case. Now, calculators are not all uniform in the way that they require you to enter exponents. You have one of two symbols on your calculator, probably, for dealing with exponents. The first one might look like this. X with an exponent of y on it, or vice versa, y with an exponent of x on it. The other button that you might have on your calculator, depending on the manufacturer of the calculator, is you might have a little caret. Okay? Everybody have one of those too? Okay, let's evaluate 5 to the third on your calculator, make sure that we're all on the same page there. The first thing you do, and this again, my instructions aren't consistent for all calculators, but on most calculators, you'll type in the base first, then your power button, and then the exponent on there. Sometimes that's reversed, but I think in this case we're always going to enter 5 to the third power, and you should get a value of 125. 5 times 5 times 5 is 125. Everybody coming up with that? Make sure you got your calculator down there, no problem. We're going to deal with how exactly to handle the significant digits in just a minute. But 6.500 squared. 6.500 squared. Take a minute on your calculator and square 6.500. Now, this one, you'll oftentimes, many calculators have just an x squared key. An exponent of 2 occurs so often that many calculators just dedicate it its own key. And if something's squared, you can just hit that one and it automatically enters an exponent of 2 on there and computes it. If you don't have that button, that's no problem. You just do what we did in the last example. 6.500 and then your exponent key 2, and what do you end up with here? 42.25. Yep. Incidentally, if you have an even exponent, what do you know will always be true about the value of that expression? As long as you have an even exponent, what will always be true about your answer? You may know what that won't necessarily be odd. Kyle?
I think it always is either 5 or 0.
Nope, that's not necessarily true either. But it will always have one property. I'll let you think about that. I'm going to ask you that question again in just a minute. Here's a slightly different case. Suppose we have this, negative 1.500. We're going to raise that to the third power. What? Negative 1.500 to the third power. Now on your calculator, maybe you've worked with negative numbers on your calculator, maybe not. Some calculators require that you enter the 1.500 and then hit the negative key to show that that value is negative. Some require that you enter it first. But beware on your calculator that you do not use the subtraction key. The subtraction key is an operation. That does not represent a negative numbers. You want to look for a key that has a smaller equal sign, a smaller negative sign, or sometimes it's in parentheses, or sometimes it even is plus minus to change the sign of the number. So take a minute, make sure you can enter negative 1.500 in your calculator, and then raise that to the third power. And what do you come up with for this one? Negative 3.375?
For the squared one, or the even power will always be positive.
There you go. Yep, that's exactly what it is. This one turns out to be negative 3.375. Even powers, in this previous example, will always turn out to be positive. Because if you think about this, if this were a negative value, but you're always multiplying it by an even number, those negative signs will always cancel off, and you're always going to have a positive value. If it's odd, it won't. If you've got a negative base but an odd exponent, it'll always turn out to be negative. Okay? And one more here before we move on. I'd like you to evaluate 9.0 to the 3/2 power. Now, certainly you wouldn't have to enter this as a fraction. You could recognize that 3/2 is just what decimal value? 1.5. You could type 9.0 to the 1.5 power. But I want you to be able to use all the features of your calculator. You should have a fraction button on your calculator. It's usually represented by this varies widely by calculator manufacturer, but some of them have A, B, C button that shows a little fraction like that, and usually A, B, and C are the letters used. That's probably the most common one. But take 9.0 and raise that, hit your exponent button to the 3/2 power. Anybody not find the fraction button on your calculator? If you have a graphic calculator, it will not have it. So what you do is you open a parentheses, 3 divided by 2, and then close your parentheses. Same thing. Yeah, graphing calculators don't have a fraction button. They do have in the drop-down menu a way you can get at it, but it's more trouble than it's worth. You just type it in using parentheses. What does this turn out to be? Should be 27. Type in 9.0, and then you're going to do your exponent button, caret or x to the y. And then you'll type, you won't want to type 3 divided by 2. You could do parentheses 3 divided by 2, but then you'll type 3 and then your fraction button, 2, and you should get 27. Work? Okay, good. Or failing that, you can, to be efficient, you could just say, oh, well, 3 halves, that's 1.5. Type in 9 exponent 1.5, and that's a quick way to get the same result. You just want to make sure you can use all the features, and then you can choose to use them however you want. No? What are you getting? Holy cow. I'll bet you what it's doing is it's taking 9 and cubing it and then dividing by 2. Are you putting this in parentheses? Use your left parentheses before you type the 3 and then the right parentheses after 2. Sometimes that fixes the problem if it's an order of operations thing. Okay, good. Usually if we're dealing with fractional exponents, we're doing some sort of algebra and the calculator won't work anyway. If we're actually doing computation, we would usually treat these as decimals. Okay, moving right along. You can have a base that has a negative exponent, and a negative exponent usually represents repeated multiplication by the reciprocal of the base. You could say that a negative exponent represents repeated division, but that could be misinterpreted. So, for example, what we have up here, from what we just saw a little while ago, 10 to the 4th power would be 10 times 10 times 10 times 10, whereas 10 to the negative 4th power is equal to 1 over 10 times 1 over 10 times 1 over 10. Now, that's going to give you another way to deal with negative exponents. Here's another case. 3 to the negative 2nd power. 3 to the negative 2nd power is the same as 1 over 3 times 1 over 3. The negative sign says it's the reciprocal of 3 multiplied by itself, or squared. Now, if you take 1/3 times 1/3, let's work on this bottom case here for a minute. If you take 1/3 times 1/3, what is that really the same as? There's several different answers you could give me, but what is 1/3 times 1/3? How could we rewrite that in a simpler way? You could write it as what? 1/9. You could write it as 1/9, or you could rewrite this as 1 times 1, which is 1, over 3 times 3, which is 3 squared, right? It's the same thing. So what that means is we've just established a relationship. 3 to the negative 2nd power is really just 1 over 3 squared. We could say, for example, if we had any number to the negative 3rd power, that's the same as 1 over x to the positive 3rd power. Or we can make a general rule and say that anytime we've got a base with a negative exponent, we can rewrite it as 1 over the same base with a positive exponent. That's the punchline. Now, ultimately, what this allows us to do is enter the value into our calculator several different ways, and we're going to do some examples of that shortly. Now, this ties in with what we were doing yesterday a little bit in regards to reciprocals. From yesterday, you remember how you take the reciprocal of a number? How do you do it? Put it underneath 1. Well, that gives us a new notation for writing a reciprocal. For example, what's the reciprocal of 5? 1/5. If we have the number 1/5, we can rewrite that using an exponent. This is the same as 5 to the what power based on this rule? 5 to the negative 1 power. Here we've just got one factor of 5 down there. That's the same as 5 to the first power. So that's the same as 5 to the negative 1. So we can say that in general the reciprocal of 5 is 5 to the negative 1. Putting a negative 1 exponent in a number always implies that we're talking about its reciprocal. In general, we can say that any number to the negative 1 power is the same as the reciprocal of that base. Now look on your calculator, and that function, the reciprocal function, is used so often that it also frequently has a key dedicated to that purpose. It's going to appear one of two different ways on your calculators. I sure wish the calculator companies would have a meeting in Jamaica, all get together and agree on what their buttons were going to look like, because they don't. One thing that this might look like is this. That, of course, as we just said, is a symbol for reciprocal. You might have that one. Anybody have that button on your calculator? The other one that you might have, and this is the one that I have on mine, is 1 over x, which is the other symbol for reciprocal. So for this one up here, for example, you could just type 5 and then hit either one of these buttons, whichever one you've got, and it'll tell you what the reciprocal of 5 is. That'd be 1/5, or of course the decimal equivalent is 0.2. Again, a shortcut that's handy to know how to use. Okay, let's stop there for just a minute. Questions about anything we've done so far? Everybody got a calculator doing everything that we've done so far? Okay. Well, moving right along. Significant digits. How do we handle significant digits? Because I know you were wondering. You're thinking, well, how do we handle significant digits? All the examples that I put up on the board so far were kind of fixed to work out right. I chose them so that the significant digits always worked out right. But in general, when you're evaluating an exponential value, the number of sig digs in the base determines how many sig digs in that value after you compute it. In other words, you keep the number of sig digs in the base. The number of sig digs in the exponent does not matter. Let's do a couple of examples. Now what we're going to do is check both that you're using your calculator the right way, which now probably all of you are, but also that we keep the correct number of significant digits. Here's the first one. Let's evaluate 26.37 with a power of 1.4. Take just a minute and do that. And you're going to get a screen full of numbers because this doesn't work out neatly. So we need to decide, all right, well, what are we going to round this off at? Your screen should say 97.6234567 Well, I didn't notice, but it's got a whole string of consecutive numbers in there. 2, 3, 4, 5, 6, 7, 9. That may have been 8, 9 when the calculator cut it off. Isn't that interesting? Maybe not. Okay. Well, how many sig digs are in your base? 4. So you keep 4 in your answer, and so we should call this 97.60. Cut it off there. Doesn't round up, so 62 would be the correct value to report. That keeps the proper number of sig digs in the computation. One more for practice. I'm going to give you another one. I want you to tell me what the correct answer with the proper number of sig digs would be here. The second one is 0.096 to the fourth power. Take a minute. Calculate the value of 0.096 to the fourth power with the proper number of sig digs. 0.000. One more? That's right. 2 sig digs here All these zeros are only placeholders. All they're doing is pushing the decimals in there. And so here's our 2 sig digs in the answer. That's correct. 0.000085 is the right result. Seems odd, doesn't it? Oh.
The negative power on there.
Well, maybe it doesn't seem odd to you. I always thought, I remember I learned about physics or significant digits when I was in a physics class, and this type of problem troubled me. I kept thinking, how can you start out with just 3 decimal places and do a computation and end up with 6? It follows the rule, but it seems counterintuitive. I said that was the last problem. I just thought of one more problem I want you to do. I want you to evaluate 5,000.0 to the second power. Report that answer with the correct number of sig digs. I'm going to give you a minute to do that. This is a little bit tricky. One, I did it because it is the problem that a lot of you got wrong, similar to it. But there's another reason that this is a good example. Take just a minute and see what you come up with here. Any claims to correctness? 25. 25 million? 0.0. That's interesting. I wasn't expecting you to say that. No. Why isn't it 0.0? I hadn't thought about that, but I'm glad somebody said it. Why isn't it point? How many sig digs have you got here? How many would you have here? You'd have 9. You'd have 2. That one would be significant, and so you'd have 2, 3, 4, 5, 6, 7, 8, 9 sig digs. So that's way too many sig digs. Now, we just talked about this on the first day, and it's not used often in most textbooks, but how would you show? You can't just leave it like this, because this is only 2. What is it? Who said that? Oh, okay. That's right. Remember, if you've got some zeros that are significant kind of midstream here, you use a line to show where the last one is. So we would say we want to keep 5 sig digs. 1, 2, 3, 4. That would show that this 0 is significant. That makes these 2 stuck in between. There's 5 sig digs. That would be the right way to write it. Oh, I see why you came up with 25,000, because you were counting the sig digs, right? Yeah, you can't just drop them, otherwise you get a completely different number. Yep. Right. Okay. Kyle.
Well, if it's 5,000.0, that's an exact number.
No?
You gotta repeat the question.
Nope, it's only precise to the nearest. Thank you. Kyle asked, thank you. Kyle said, if it's 5,000.0, that's exact. It seems exact, but here's an example of why. Don't put this in your notes, but this is actually a great point to make. Do this on your calculator. 5,000.0 only indicates that we're rounding off to the nearest tenth, right? Our precision ends at the tenth. That's from our discussion yesterday. Just do this. Just try this on your calculator. Enter, I hope this works now, otherwise I'm going to have egg on my face. Enter 5,000.01. Okay? Now, would this be an acceptable approximation if that was the real value? This would be fairly accurate, right? And precise to the nearest tenth. Okay? We could have even said 5,000.02 and it would be okay. Now take this and square it and tell me what you get. You get 25 million. So, this says that it's precise out to what place? Out to right here, right? And sure enough, it really is. It is precise out to here. But if we vary from that 0 by more than just a little bit, then our answer won't be accurate beyond this point anymore. You see what I'm saying? So it preserved the correct amount of precision. We were precise to the nearest tenth here. We could wander a little bit in the hundredth, but we're precise to the tenth, and the answer was precise to the right spot. Beyond that, it was a little wrong. Make sense? So it preserves it just the way it should. That slight error will make a much larger error when you take such a large number and square it. Good. That was really a good point. I should write that in my notes and make sure to hit that next year, because that was really a good point that I had not thought of before. Well, moving right along. Roots. Actually, there we go. Roots are very closely related to powers. They're like they're a brother of a power. Every root is really just a power in disguise. It's written a different way. You can say that in general, if you have some base a to some power and it equals another number, then we can rewrite that as a root. And I'm going to write that using some real numbers to help it be a little bit easier to think about. Do you agree that 2 to the third power is equal to 8? 2 times 2 times 2 is definitely 8. Therefore, we can say that the cube root of 8 is 2. Or here's another one. 3 to the fourth is 81. Since 3 to the fourth power, 3 times 3 times 3 times 3 is 81, we can write that, we can write the radical or root statement that 81, the fourth root of 81 is equal to 3. But here's the kicker. Negative 3 to the fourth power. Remember what happens no matter what if you got an even exponent? It's going to be positive. So what's negative 3 to the fourth power? 81. And so the fourth root of 81 is actually plus or minus 3. Either one of them works. Usually, when we take a root, not always, but oftentimes we're only interested in the positive root, and we call that the principal root. And I think we're going to get to that in just a minute. Make sure that yes, we're going to get to that in a later slide, so I won't dwell on that too much now. A little bit of terminology. I already used some of it, but let's take that example right there. The fourth root of 81. First of all, anybody know what that 81 is called? That 81 has a name. Everybody remembers what a base and an exponent and a power are, but anybody remember what that 81 is called? That's all right. It's called the radicand. It's the radicand, which you're going to find, I'll try and point them out when I come across them, but there are a lot of mathematical terms that would make great names for cars. In recent years, this has actually started to occur. The matrix, mathematical term, it's not from the movie, it's from math. And there's a vehicle called the Matrix. The Ford Focus is another one. Focus is from physics, it's also a mathematical term. They stole it for cars. I thought radicand would be a great name for a sports car. Or maybe a luxury car like the Chrysler Radicand. Well, anyway. You've dealt with this before, but it's worth noting at this point. If you don't have an index shown, you have to assume that that is what kind of a root? A square root, right. In general, you could say that this means the square root of 17. Those two mean the same thing. Never does the absence of an index mean anything other than 2. Okay. moving right along here. A couple more notes about powers, and then we're going to wrap up this topic. Here's the statement that will show that every radical can be written as a power, and every power can be written as a radical or a root. Radical and roots are essentially different names for the same topic, the same type of thing. The nth root the nth root of x can be written as a power of x to the 1 over nth power. Now we'll look at some examples of that with numbers to make it a little bit easier to see. Now, just a minute ago, we computed this, or we discussed it. Anybody remember what is the fourth root of 81? Plus or minus 3. Your calculator, if there is more than one root, if there's a positive and negative root, beware, because your calculator will only give you the principal root. They'll only give you the positive one. So here's what I want you to do. I want you to compute this root on your calculator without using the radicand sign. I would like you to take this and write it as 81. What would the power on this 81 be? 1/4. The fourth root of 81 is the same as 81 to the 1/4 power. You know how to do this on your calculator. Go ahead and do it. Take 81, raise it to the 1/4 power. Of course, if you don't want to enter the fraction 1/4, you could type 0.25, and it better give you a result of 3. Now, technically, that's plus or minus 3. We have to note that. But your calculator says that it is 3, so you have to be aware and watch for that. But I want you to also be able to use the radical button on your calculator. So let's find the same value without using this method, but actually by entering the radical. You should have a button on your calculator that looks something like this. And not all calculators have a button of this style. Some calculators assume that you will enter it this way and don't give you this button. But they will have something like that, the nth root button. It's oftentimes the shift or second function on the same button that you used earlier, and that's your exponential button, since they are opposites after all. So if you had an x to the y button or a caret button, sometimes the shift or second function will get you that root button. Anybody find that? Okay. What do you have?
I have to shift and use that button.
Okay, yeah. On some of them, it could be an x over here. There's a lot of variation in how you enter this in calculators, but most of them will ask you to enter the index first, and then this button, and then the, what's it called? Radicand. So give it a try. Type in 4, and then this button, and then 81. If that doesn't work, if you get some screwy number, reverse it. Some calculators it's reversed, which doesn't make a lot of sense to me, but that doesn't matter. Did you get a result of? Good. And of course, we know that it would be plus or minus 3, but your calculator only reports the principal root. This clarifies what we spoke of a little bit earlier. Sometimes the root of a positive number can have more than one value. Those are, in general, if we have a positive number and an even index. If we have a positive number with an even index, there will be 2 solutions. And so when that occurs, it could be plus or minus. And we refer to the positive one, which is often but not always the one that we're interested in. That's called the principal root. And again, why is that true? Think of a simple example. It's true that 5 squared is equal to 25, but it's also true that negative 5 squared is equal to 25. this is going to become our radicand, and we would say that the square root, even index of 25, positive number, could be either plus or minus 5. Principal root would be the positive one. Your textbook usually only gives the principal root. Some of your homework for today will ask only for the principal root. Watch out for that. And let's wrap this up. How do you handle significant digits? Well, essentially, when we're taking any kind of a root, it's the number of sigdigs in the radicand that will determine the number of sigdigs in the value of the root. So before we paid attention to the base and counted sigdigs, now we're going to pay attention to the radicand. Now, ultimately, how you evaluate these, if you find that you prefer treating them as exponents more than using the radical button on your calculator, it's no problem. Whichever method you find to work is fine with me. Let's evaluate these with the proper number of significant digits. Let's take the fifth root of 63.7. And then after you do that one, I'd like you to evaluate 63.7 to the 1/5 power. Well, how many sigdigs are you going to be allowed to keep for either one? 3. Do you see why, if we pay attention to the base when doing exponents, it's really the same as paying attention to the radicand when we're doing roots? They play the same role. And so we can keep 2 sigdigs. If you round off the value of that root at 3 sigdigs, 2.30 is correct. And of course, this is the exact same question, just written a different way, 2.30. Good. How about the fourth root of 0.5641? You can rewrite that as an exponent if that's your preference, but I'll just leave it like that and ask you to evaluate it. How many sigdigs in your result? You should have 4. I'm going to leave a little space here out in front of that number. 0. Okay, plus or minus, right. Since there's a positive radicand and an even index, that's actually plus or minus 0.866. Now your homework says just find the principal root, and then you would not have to worry about the plus and minus. You would assume the positive one. Okay, last one. Got this one done. We're going to call it a day. I'd like you to evaluate the cube root of negative 32.4. The cube root of negative 32.4. Cube root of negative 32.4 will have 3 significant digits. What did you come up with? Negative 3.19. Now, how could you check that? You're skeptical. Gosh, a negative root, that seems odd. How can you check that to make sure that it's right? You could take and say, go back here, take negative 3.19 and go ahead and raise that to the 3rd power. What had you better get? Negative 32.4. Now, you're not going to get negative 32.4 exactly because we rounded it just a little bit. But you do get 32.46, which is pretty darn close, so we're good to go. All right. What we're going to do tomorrow is we're going to combine all these operations, work with sigdigs. and do a whole series of operations and pay attention to the proper order of operations and the right number of significant digits.